A well-written SQL query can take millions of floating, disconnected data points and snap them into a coherent structure in milliseconds. But a database engine doesn't question your logic. It executes exactly what you type. Use the wrong command, and you might silently delete thousands of vital records, or bloat a simple server request until the system crashes. The true complexity of relational databases lies in matching the specific combination tool to the right business scenario. Look at these two identical starting tables. One operation gives you 50 clean results. Another gives you 5,000 duplicated errors. Today, we are going to break down the mechanics and the trade-offs of three core tools: inner joins, outer joins, and unions. We'll also look at edge case variations, like the theta join, so you know how to protect your system's performance when the logic gets complicated. By the end of this, you won't be guessing which code to write. You'll be engineering data architecture on purpose. We start with horizontal linking, pulling details from two distinct tables to stitch them side by side. If you need absolute precision, use an inner join. It demands perfect equality. Any row without a direct matching partner simply vanishes. You get a highly optimized, clean dataset. But if you are trying to run a report looking for missing data, those silent drops ruin your analysis. When your priority is data retention and completeness, you switch to an outer join. An outer join forces the database to keep all the unmatched records from your primary table. Even if the secondary table has nothing to offer, primary data stays intact, filling the gaps with empty null values. This prevents accidental data loss, making it perfect for auditing. The trade-off is developers now write extra code to handle all those incoming null placeholders. Choosing between an inner and outer join is a direct business decision. You are prioritizing strict accuracy, or complete auditability. Once you decide to join horizontally, you have to tell the database exactly how to measure the match. You set the condition. The baseline is the Equijoin. This links tables based strictly on exact equality, like matching a customer ID in Table A to the exact same ID in Table B. Computationally, this is highly efficient. The engine spots the exact match and moves on. But it is entirely inflexible if you need to compare a range of numbers. For complex range-based logic, you need a heavy-duty solution, the theta join. It uses inequality operators to find data, linking single data points across varying ranges. It allows for advanced logic, but it forces the database to work much harder, burning more processing power to evaluate the ranges. And speaking of processing power, we have to talk about the cross join. A cross join produces a complete relational product, mechanically multiplying every single row in Table 1 by every single row in Table 2. If you need to generate a deliberate matrix of every possible product combination, it does the job. But if you trigger a cross join by mistake, the exponential math devastates your server's performance. Optimizing a query means picking the strictest condition type that answers your business question without wasting server cycles. Beyond horizontal links, SQL allows you to grow your dataset vertically. Instead of stitching tables together side by side, we stack them on top of one another. To do this, we use the union command. It abandons related keys entirely, taking result sets of queries and stacking them. By default, it selects only distinct values, filtering out duplicates. But to pull off a vertical stack, you follow strict structural rules: same number of columns, the same data types, and the exact same order. Ignore that rule, and your database will reject the query entirely. You use union to consolidate identical data structures, like appending last year's sales to this year's. You do not use it to discover new relationships between different entities. Query optimization actually starts before you write code. It begins the moment you conceptualize the final shape of your data. Let's map this out. Suppose you are a data analyst. You have two separate mailing lists with some overlapping users, and you need one clean master list. Because you need to append identical records and drop the duplicate safely, you follow the path straight to the union command. Now imagine you are an app developer. You are building an e-commerce dashboard that must only display users who have successfully completed a purchase. You need to combine related user fields, and you want to actively hide the unmatched records, the window shoppers. The clear choice is an inner Equijoin. It's computationally light and cleanly drops the empty rows. Finally, suppose you're an auditor. You're generating an inventory report, and it absolutely must show total stock, including the items sitting on shelves that haven't sold yet. An inner join would silently hide that unsold inventory, skewing your entire audit. You need an outer join to keep those unmatched records visible. Treat these operators as distinct, specialized instruments. When you know exactly how they process data, you'll not blindly swing a hammer